Hello everyone, my name is González-Docasal and I work as a researcher in speech technologies at Vicomtech, a non-profit applied research center from Spain. The work that I will be presenting is titled Towards a Natural Human-Robot Interaction in an Industrial Environment, which is the result of the collaborative project Languilleoc between Vicomtech, Techniker and Tecnalia, applied research centers. This is the outline of the presentation. First, I will introduce the work, then I will explain the system built for this project alongside its modules. Afterwards, I will proceed with the evaluation of the system performed on an industrial environment by a set of testers, which will be subdivided on a quantitative evaluation and a qualitative evaluation, and finally, I will summarize the final conclusions of our work and explain how the system and the evaluation could be improved in the future. One of the main challenges of Industry 4.0 relies on human operators using natural language and gestures as a way of controlling robotic agents in order to increase productivity. Some of its advantages are the following. It has no specific syntax, different voice commands or expressions can be used to order the same task. Saying a voice command like move, for instance, or pointing a piece is faster than selecting a command from a displayed menu. It requires nothing more than a camera or a microphone at hardware level, and the operator can be free-handed. But it should also fulfill at least the following requirements. The robot should be able to understand what the operator wants to do. It should maintain the safety of the personnel and equipment around the robot, and it should also perform correctly in adverse environments, like nausea-acoustic environments or low light conditions, aspects that pose continuous technological challenges. In order to advance and contribute to this task, in this work, we present a system that allows a natural interaction between a human and a robot using free voice commands within a manufacturing scenario. It was evaluated using two automatic speech recognition systems based on different architectures, a more traditional Kildal-based ASR and an end-to-end ASR system. Moreover, the system was tested over two different mobiles and therefore two different microphones and using bilingual speakers with strong Basque accent in Spanish. It should be noted that the system interaction was evaluated in a manufacturing scenario within an industrial environment. Here you can see the main architecture of the evaluated system. It consists of different modules. The audio acquisition module is responsible for gathering the voice signals, and it's composed by the mobile phone with its microphone in addition to a software application that allows the recording of the voice commands. This audio acquisition module is connected to the next ASR module through REST web services. The ASR system, which provides a background remote service, is in charge of transcribing the input voice command and sending it to the next module. The semantic interpreter passes the key elements in the transcription with the aid of the knowledge manager, which converts them to robot commands. And finally, the fusion engine merges the outputs of different sources, like gestures, with states out of the scope of this work. For the audio acquisition, two different microphones were used. They were the built-in microphones of two Android phones, Xiaomi Mi A2 and Motorola Moto G5. The audio was recorded and stored on 3GPP format with AAC codec at a bitrate of 96 kilobytes per second and a sampling rate of 16 kHz. It is also shown a screenshot of the Android application that served as the main communication interface between the operator and the system. Through this application, the audios were recorded and sent to the ASR service in order to transcribe them. The first ASR system to be tested was based on the Kali open source toolkit. The acoustic model was built with the NNet3 DNN setup and using the so-called chain model based on a factorized time-delay neural network. We used a input of 40-dimensional vector composed by MEL frequency capture coefficients along with their deltas and delta-deltas. Several enhancement techniques were also used, such as linear discriminant analysis, maximum likelihood linear transformation, speaker adaptive training, and speed and volume perturbation in order to make the acoustic model more robust against any acoustic disturbances. The language model were 3-gram models with modified Knesset-A smoothing, estimated with the KNLM toolkit. This system was trained on a total of 283 hours in Spanish, consisting of 132 hours from the Corpus Savas, composed mainly of broadcast news from the local Vax television, ATV, 21 hours from different type of TV programs from the local Basque television, 103 hours of different TV programs from the national Spanish television RTVE, liberated at the Albaicín Challenge 2018, 20 hours of microphone speech from Mozilla's Common Voice project, and 7 hours from the Albaicín and Moltex Small Cobra. Finally, the language model was trained with 20 million words in 860,000 sentences from general news domain. The second ASR system evaluated was based on the Baidu's Deep Speech 2 architecture that served as the acoustic model, and it was composed of two 2D convolutional layers, 5 gated recurrent unit layers, and the final fully connected layer. As input, it used the whole MEL spectrogram of the audio as an image, and the output labels were the characters. The enhancement techniques that were used are spectrogram augmentation, time dilation of the input signal, and noise injections with the aim of gaining robustness against noisy artifacts. The original media corpus was transferred through a telephonic channel, and the end-to-end acoustic model was trained both with the media and telephonic corpora, and afterwards the model was fine-tuned to the media corpus, which fit the audio conditions better. Finally, an external 5-gram statistical language model was used to rescore the initial hypothesis of the end-to-end acoustic model. The end-to-end model was trained on 795 hours in Spanish, consisting on 132 from the previously explained Savas corpus. The acoustic data was augmented twice as big when transferred through the telephonic channel, and 3 more times using time dilation by 0.9 and 1.1 factors. Finally, the corpus for the language model is the same as above, composed by 20 million words and 860,000 sentences from general news domain. The semantic interpreter's goal was to understand what was the given order from the textual transcription of the ASR. It employed frilling and a set of linguistic rules in order to determine the requested command. These rules had been obtained by manually parsing queries and implementing the most common syntactic patterns. With this and the information of the knowledge manager, it selected the most suitable command. The knowledge manager is an ontology defining OWL that models the environment, the capabilities of the robot and their relationships. It includes the basic actions of start, stop, resume and move, as well as information about the scenario, such as which operation was being executed, if it involved the robot, if the robot was waiting for a human operator to complete a task, etc. Finally, the Fusion Manager decides which is the correct operation from all the incoming sources. In this project, we only use the audio signal. The developed system was tested on a real manufacturing scenario at Technica's facilities. The evaluation consisted on a collaborative work between the robot and a human operator, and the main task consisted of assembling and screwing different parts of a manufacturing piece. While the robot assembled the parts of a piece, the human operator was in charge of screwing them. The operator guided the robot using his voice during the whole process, and the robot waited for the operator to screw the piece and continue once the corresponding correct commands were received and understood. Here you can see a picture of the scenario in which the proposed system was evaluated in several trials between the robot and different operators, and within an industrial environment. Different manufacturing machines were around this evaluation scenario, which was continuously contaminated by a high and varying acoustic background noise. The evaluation was performed by 27 volunteers from a local manufacturing school, composed of 21 males and 6 females, whose ages ranged between 21 and 49, with an average age of 25.4. The volunteers were divided into 2 different groups. The first group tested the Kildal ASR system and recorded 27 audios with the Motorola Moto G5 and 26 audios with the Xiaomi Mi A2, summing up a total of 53 audios of voice commands. The second group evaluated the end-to-end ASR system and recorded 23 audios with the Motorola Moto G5 and 26 with the Xiaomi Mi A2, for a total of 49 audios of voice commands. The first part of the quantitative evaluation consisted of measuring the performance of both ASR systems on both microphones. The metric used was the word error rate, which corresponds to the total of error, substitutions, deletion and insertions divided by the total of words in the reference. As you can see, using the Xiaomi Mi A2 microphone, we achieved a word error rate of 14.29% using the Kildal based ASR and 14.52% with the end-to-end based one, which have very similar results. On the other hand, the best results were achieved on the Motorola Moto G5 microphone, scoring a word rate of 3.13% with Kildal and 8.86% with the end-to-end. First of all, as it can be appreciated looking at the results, the combination with the lowest word rate is Kildal and the Motorola Moto G5. It can be also seen that Kildal performs better than the end-to-end system in both scenarios. This could be due to the fact that Kildal was trained with more varied data that could have contributed to a more robust acoustic model against the noisy background conditions. Also, it's worth noticing that in an environment with generally short voice inputs, the word rate values increase faster than in other scenarios. This is supported by the fact that out of the 102 voice inputs processed by the ASR systems, 81 had no transcription errors at all. In order to evaluate the semantic interpreter, we separate the correct transcriptions, those that had 0% of word rate, and the incorrect transcriptions. The semantic interpreter performed correctly on 77 out of 81 correct transcriptions, failing on only one and not giving an order on 3. These, categorized as no order, correspond to transcriptions like OK or faster. Also, from the incorrect transcription, the semantic interpreter was able to select the correct order on 12 out of 21 utterances. Obviously, transcription errors influenced the system negatively. When the sentence did not change too much, the system was still able to infer the correct interpretation, for example, when a stop word went missing. It is worth noticing that none of the utter commands was out of the scope of this evaluation procedure. In this slide, we separate the evaluation from the previous slide so that the microphone and the ESR system information are also shown, resulting in an evaluation of both the ESR system and the semantic interpreter simultaneously. As the data shows, the best performance is achieved using Kildal and the Motorola Moto G5, which is the combination that has higher percentages of correct transcriptions and orders. For the end-to-end recognition system, both devices perform similarly in terms of final correct orders. In order to evaluate the system quantitatively, a questionnaire was given to each of the participants. The difficulty of the task was measured with a question in a scale from 1 to 7, being 1 very difficult and 7 very easy. The results gave an average score of 6.42 and a standard deviation of 0.76, thus classifying the task as easy. In order to measure the trust on the system, the Charles-Lambeau scale was used. It consists of 10 questions ranging from 1 to 5 with a maximum value of 50 points. The score obtained with these measurements was 41.1, which indicates a high trust on the system. For the usability measure, the questionnaire contained the system usability scale, also consisting of 10 questions with a maximum score of 100 points. The score obtained on this scale was 75.93, which corresponds to an acceptable usability level of grade B. Finally, an additional survey was filled with the participants on 9 questions ranging from 1 to 5. The users most agreed on the following statements: the robot did what I ordered, working with the robot was a good experience, and the voice recognizer understood well what I said. Some conclusions of the evaluation. First of all, as seen by the data, the most robust ASR system was Kildal with the Motorola Moto G5. It should be noticed that its acoustic model was trained with more varied data that could have contributed to a more robust acoustic model against the noisy background conditions. Also, on short inputs, word rate values increased faster than in other scenarios. The semantic interpreter was able to deduce the correct order in the majority of the utterances. Having correct transcription, it deduces the correct order in 95% of the cases, was performed correctly on 87% of all given utterances. Obviously, transcription errors influence negatively the performance of the semantic interpreter. Finally, the users classified the task as being easy to use. Additionally, the system built a high level of trust and a good point of usability among the volunteers. As a future work, a development of the system in a real industrial environment is proposed. The system should be able to behave correctly in a majority of situations, as it has been proven in the results, reported by the high acceptance of the users in the evaluation. The system could also be provided a higher level of complexity for a more complete and fluid human-robot communication in a safe environment, such as a complete dialogue system with answers from the robot to the user. Finally, A set of biometric sensors measuring the physiological parameters of the operators during their interaction with the robot could improve the quality of the evaluation for further conclusions on acceptance and comfort of the proposed system. I would like to thank you for your time watching this presentation on behalf of everyone on the team, and we look forward to answering any questions you may have.